Deformations of steel and plate beam to column joint when subjected to simulated steady state and transient state fire heating regimes by Mariusz Maslak and Michal Pazdanowski. The scope of my presentation is as follows. Background of the research, description of the joint modeled and analyzed, data used in numerical simulations, details of the numerical model, program of simulations conducted, presentation of selected simulation results, discussion of model credibility in terms of obtained results, and finally conclusions. The bending moment rotation angle relationship is temperature dependent and its evolution in real fire is dependent on actual fire development. This in turn depends on many factors which are of random nature and beyond our control. Thus, two bounding scenarios have been selected for application, the steady state and transient state heating regimes. In the first case, the structure is heated to the predetermined temperature and then loaded statically to the destruction, while in the second one, the procedure is executed in reversed order. That means the structure is statically loaded to a given level and then heated to destruction. In our numerical simulations, the destruction would be considered as a failure to converge to an equilibrium during an iterative increase in the load applied to the model. The analyzed structure depicted here consists of a 2-meter-long cantilever beam made of an IPE 240 bolted to a column made of an IPE 360. The part of the column flange directly in contact with an end plate has been replaced with a plate 30 mm thick, made of the same steel grade as the column and beam. This was intended to limit the joint deformation to the deformation of the end plate itself. Details of the joint are depicted here. The beam is welded to the end plate with a fillet weld, while the end plate is bolted to the column flange with 6 M20 pre-stressing bolts. The actual material data for the components of the joint, that means the column, beam and the end plate, have been determined experimentally based on the uniaxial test conducted at 20 degrees centigrade. Material constants for the bolts have been assumed as for 10.9 class bolts according to the code. It has been assumed that the bolts have been tensioned to a 172 kilonewtons each at 20 degrees centigrade. The evolution of material constants for temperatures higher than 20 degrees centigrade have been assumed to follow the curves defined in the Eurocode, namely Eurocode 1993-1-2 EC3. The structure has been modeled in Abacus environment as a 3D object consisting of 8-node C3D8R brick elements with reduced integration and hourglass control. It has been assumed that the bottom plate of the column is fixed and the beam is restrained to deform in vertical plane only. The load is applied as a vertical traction applied over a small area at the distance of 2 meters from the joint face. The problem is always treated as a static one, this meaning that all rate-dependent phenomena are expressly excluded from the analysis. The contact is modeled with express definition of contact surfaces, where sliding is allowed and assumed friction coefficient value of 0.5 is taken into account. It is also assumed that this friction coefficient is temperature independent. No material overlap is allowed. The assumptions listed here strongly affect the calculation time. We are interested in dependence of results on the end plate thickness, so 4 end plate thicknesses are considered as indicated. At first, the application of static load at 20 degrees centigrade is considered to obtain the information on the simulated bearing capacity and moment rotation relationship to classify the joint according to the Eurocode. According to the rules prescribed by Eurocode 1993-18, the joint fitted with 20 mm end plate behaves as rigid within the whole scope of this loading program. The joints fitted with 10 and 8 mm end plate follow this behavior up to about 50% of their total bearing capacity and later on change to semi-rigid behavior, while the remaining joint fitted with 6 mm end plate from the beginning behaves as semi-rigid. For the steady-state heating regime, the 6 listed heating temperatures have been considered, while for the transient-state heating regime, 4 listed loading levels have been considered. It has always been assumed that the temperature of all structural components is the same in their whole volume during the analysis. The results of steady-state heating regime simulation for the joint fitted with 20 mm thick end plate are depicted here. These seem to indicate that when the joint is heated to the relatively low temperature of 400 to 600 degrees centigrade, the local loss of stability in the bottom flange of beam is a critical factor, while in higher temperatures of the 700 to 800 degrees centigrade, the destruction is initiated by the shearing deformation of the column and compounded by plastic deformation of the beam. In the highest temperature, around 900 degrees centigrade, the residual rigidity of the beam is so low that it behaves similarly to a flexible tendon subjected to gravitational loads. The results depicted at the left show the rotation angle bending moment relationship for all the end plate thicknesses considered at selected temperatures under steady-state regime, while the right graph depicts the results obtained for the joint fitted with the end plate 20 mm thick. Quite obviously, the higher the end plate thickness, the higher the joint bearing capacity and rigidity, but the lower ductility. While at the lower temperatures of the spectrum considered, the difference in joint bearing capacity between plates of different thicknesses is very pronounced, at the higher temperatures this difference is much less visible. The different locations of the starting point of the rotation angle bending moment curve reflect the initial rotation angle induced by application of pre-stressing and heating. The graph depicted at right seems to indicate that at least for the joint fitted with 20 mm thick end plate, the highest ductility may be expected at around 700 degrees. Again, different locations of the starting point of each rotation angle bending moment curve reflect the initial rotation induced by application of pre-stressing and heating. The simulations following the transient-state heating regime may be used directly to obtain the critical temperature of the structure, that meaning the temperature at which the structure loses its capacity to support external loads. The results presented seem to indicate that for the joint equipped with the thinnest end plate, this temperature almost does not depend on the load level applied. A qualitative change may be observed for the joints fitted with the end plate at least 8 mm thick. To verify the quality of numerical results obtained, an analysis of the same loading case has been executed on 2 finite element meshes substantially differing in finite element size in the critical zone, that meaning the end plate and the column flange in direct contact with the end plate. The difference resulted in a factor of 5 ratio in the number of degrees of freedom and very substantial difference in the calculation time. However, the difference in the displacements in the end plate amounted to less than 1%. While the difference in the equivalent von Mises stress amounted to about 11.5%. The calculations on the denser mesh yielding the lower values. This is consistent with what may be expected when the displacement-based finite element model is applied. Based on those results, it has been assumed that the lower density mesh would yield the results of sufficient accuracy for the purpose of this analysis. The displacements obtained during simulation at 20 degrees centigrade have been used for comparison with the results of experiments conducted by another team. As can be seen on those pictures and graphs, the qualitative agreement seems to be very good. To conclude, two complementary fire simulations have been considered, in a sense representing bounding approaches to a real fire situation, allowing for initial qualitative assessment of joint rigidity evolution in fire, indicating that different joint destruction mechanisms may be expected. Due to the limitations of the numerical model applied, those results should be treated as preliminary. A more detailed model allowing for differences in the temperature of modeled components and more accurate modeling of prestress is under development. A comparison of the numerical results with the results of an experiment are also intended. Thank you for your attention.